We're going to finish this unit by looking at sex-linked genes, which we've mentioned before with meiosis. But a gene is considered a sex-linked gene if it's located on a sex chromosome, so an X or a Y, for instance. The father, we know, contributes the X or the Y, since he has one of each, and therefore he's the one who determines the gender of the offspring. And if you take a look at the picture, you can notice that there's a size difference between the two chromosomes. The Y chromosome is smaller, and therefore, just because of its size, it can't contain as much genetic information. The X chromosome, on the other hand, is a lot larger, and so the information for sex-linked traits are located on the X, not on the Y. So the Y chromosome mainly has the genetic information needed for male reproductive system, does not contain specific disorders or traits for anything due to its size. Around 2 months of development, the baby is going to produce ovaries if there's no Y chromosome present. If there is a Y chromosome, then obviously they'll develop testes at that point. And there are more males than females who have recessive sex-linked traits. And that's because males only have an X, they have an X and a Y. So if they have one of each, and we just said that the X is the only one that contains information for these traits, then males will either inherit the X with the dominant trait and not have whatever it might be we're looking at, like color blindness, for instance, or they're going to inherit the X that has the color blind on it. So they either are or they aren't. There is no heterozygous when it comes to a male. Females, on the other hand, you have two X's. So in order for you to show these sex-linked traits, you need to have a recessive X with another recessive X. And so mathematically, that's just it's harder to get to that point to have two recessive X's, so your chances of having those is smaller. Some examples on how we set these up: for instance, I mentioned color blindness. That is a trait that is on the X chromosome, and we're going to say that having normal vision, where you can see and distinguish all the various colors, would be a capital A, so it's dominant, and color blindness is a lower A. But because this is sex-linked, we can't just have capital A and lowercase a. We need to show what chromosome it's on. So if we have a colorblind father, for instance, we have to put an X and a Y because he is male, and then he's colorblind, which means that the information located on his X chromosome is the recessive, is the colorblind information. So his X chromosome codes for color blindness, his Y chromosome doesn't code for anything. Heterozygous mom, she has X with X because she's female. Heterozygous means different, so we have one dominant with one recessive. If we take a look at some examples then using our X and our Y system, we're going to keep with the normal versus the colorblind. And we're going to look at a heterozygous mom and a colorblind dad. So I think we just had that. We want to know the genotypes of the parents. So if our mom is heterozygous, we need to keep XX for the mom, and we're using the A for colorblind or not. Capital A and little a. Heterozygous means different, one of each. And the father, we need to have an X with a Y, since he has XY chromosomes. And he's colorblind, which means his X contains the information for colorblindness. It's a lowercase a. So we have the genotypes of our parents finished, and we are going to go ahead and separate our sex chromosomes, because like all of our genetic information, parents can only pass on one allele for each trait. So mom and dad can each only pass on one of their pieces of information, and we need to go ahead and recombine them and look at what our potential offspring are going to look like. Again, please make sure if you're doing like here where we have an X and a Y, put the X first. And if you have one of these where you had a big A with a little a, make sure you go and put the dominant one first and then the recessive. So we have our Punnett square completed, and what are the expected genotypes and phenotypes of all the offspring? So when we're doing the phenotypes, that's where we've normally been starting. We're taking a look at, are they colorblind or not? And we can't just say colorblind, not colorblind, because we also have gender in here. So we need to say how many females are colorblind, how many females are not colorblind, how many males are, how many males are not. So we have all of our choices. Now we might have 0 for some of these, but just to throw out the fact that there are 4 different possibilities, since we are adding the male and female component to that. So we only have 2 female boxes, these top 2, because we have XX and then this one's also XX. We have a big A with a little a, which means, according to our chart here, that big A is normal, so she's not colorblind. That's 1 out of 4, 25%. And then we also have female colorblind. That's 1 out of 4, or 25%. When it comes to the males, we have these bottom 2 boxes because they each have an X and a Y. We have one with a capital A, so they have normal vision, and one with a little a, so they have colorblindness. So in this case, you could have 4 children, and every child would be different. You could have a female with and a female without, male with and male without. And genotypes, if we take a look at the genotypes, notice that every single one of these boxes are different. So we have X big A, X little a, and that shows up 1/4 of our time, 25%. We have X little a showing up 25%. For sake of room, I'm not going to put both of them. I don't think it'll all fit. We have X big A and a Y, and that one also shows up 25% of the time, 1 out of 4 boxes, and X little a Y. So we have lots of unique phenotypes and genotypes when it comes to this particular example. Let's do one more. We have a normal vision male and a colorblind female. So we have a normal vision male. Let's do our X and our Y for him. And he has normal vision. So normal vision was the capital A, which is found on the X chromosome. Nothing on the Y, because the Y chromosome doesn't hold any traits for that. Colorblind female. So females, we know we need to have an X with an X. And colorblindness means that she had to have 2 little A's. A big A would have made her non-colorblind. So we know she has to have 2 recessives in order to get that. So we have the genotypes of our parents. Go ahead and, fill out your Punnett square and do that if you haven't already. Need to fix that there so I have a Y, not an X. Be careful with your letters that I can tell them apart. So we are going to fill out our boxes. We're going to put our dominant first and then our recessive if we have a capital with a lowercase. We're going to make sure in our boxes that have the X and the Y that the X comes first and the Y comes second. So our Punnett square is done. Now the question is, what are the chances that their son is colorblind? So we're only looking at just the sons. Okay, that's the only 2 boxes that we're worried about. And if they're going to have a son who's colorblind, yeah, that's going to be 100%, isn't it? This one has a little a, so they're going to be colorblind. This one has a little a, they're going to be colorblind. So there's a chance, there's not any chance that they could have a son who's not colorblind. So 100% all sons are colorblind. Now, something that I want you to understand where this comes from. Notice that for the sons, they have a Y chromosome. And hopefully we know that the Y chromosome comes from Dad. He's the only one that can pass that Y chromosome on. So this X with the little a, the colorblind X, had to come from Mom. And males, if you ever find out that you do have a genetic disorder or a genetic trait of some type that's sex-linked, then you know that you had to receive that from your mother, because she passes on the X chromosome to you, whereas Dad passes on the Y chromosome, and therefore can't give you the trait for color blindness since it's on the X. To finish up our unit, I want to take just a quick look at nature versus nurture. What this is a lot of people think, I am who I am because of my DNA. And that's not completely accurate. Obviously, your DNA is important. It does kind of set some guidelines as to how you're going to look or how you're going to turn out. But your environment can help determine your phenotype as well. So some examples. Nutrition can influence your height. We know that kids who from an early age are getting milk and all their vitamins and those types of things, that they grow up to be healthier than kids who come from families where they don't get that nutrition. We also have exercise. Okay, a person who exercises can definitely alter the look of their body by bulking up on muscle and cutting back on fat. So exercise can definitely determine your outward appearance. That your DNA isn't going to tell you that you can be that muscular. And then we also have sun tanning. So this is the same girl before and after tanning. So sun tanning can darken your skin, and it might not be permanent, but it does at least temporarily affect your phenotype. That didn't come from her DNA. Her DNA didn't say that you're going to be, have this particular skin color. That was kind of self-induced with the tanning. So there's a combination of your DNA and your environment that plays an impact on how you're going to look. And the last thing I want to mention is pedigrees, because if you are curious on any type of family history or why do I have a certain characteristic and a parent doesn't, this might be something that you could maybe take a look at. A pedigree is a diagram, and it shows you a family tree, and specifically it's showing you who in the family has a certain trait and who does not. So this would be an example of a pedigree. So these would be like your parents would be here, and this would be and the F1 generation would come next. So all of these 4 kids are siblings, brother, sister, to the parents. And then sometimes, we have siblings that get married, and so we have someone outside of the family who is married in here, and they've had 2 children of their own. That's how you kind of read through that. As far as the symbols go, squares represent males, circles represent females. So these 2 original parents had 2 boys and 2 girls, and they also go in a chronological order. So their oldest child would come first, their second, their third, their 4th child. So we know that the baby of that family was the daughter. And the shaded symbols are showing you who has the trait that you're tracking. So let's say you specifically wanted to track hair color, and you wanted to track all the people that had red hair. Well, these people who are shaded would be the people that had red hair. Or if you were tracking who has blue eyes, well, then the people with the shaded part are the ones that have the blue eyes. So anytime you see a shaded in circle or square, you know that they're the individual who has the trait, and you just need to know what trait they were looking at within that family and what trait they were tracking. And that kind of finishes up a little bit with genetics. We have a little bit more with some specific human characteristics, but just our introduction to Mendel and some Punnett squares, we're finished with this part.